Hello. Yeah, so in the last part, we were just talking about what data sets are. I feel like this topic needs a different video in itself, so I'm doing a different one. Okay. Basically, what you have is a way to configure and modify your data set, that is your raw data set, into a very PyTorch relevant data set, how Python wants it, and PyTorch wants it in a sense, right? So that is what um, we have exactly in data sets. Okay, so I was creating this data set a class which is using this get int for indexing and the length for returning the length of the data set, right? So just gonna complete that. So data set is created. So now we are passing the data set, basically taking the X-train, Y-train that's there inside, and now we are passing both of them, X-train and Y-train, into the um, training custom data set, right? And you return this guy, putting it in and done. And as soon as you are done with that, what you can exactly see here is this dude. Now it's not really iterable. You can see basically it's a object of that class, right? Comes from dataset class. You can actually see what it is. You can do this. So when you're indexing, you can actually see the element of first element of x and first element of y in a sense. Okay, so that is what it's doing. See, you can. I also printed it out. You can see it here as well. Okay, done. So it printed it out here. So the first instance from the dataset was returned when you use 0. So this indexing was done by get int. Mm. And this whole thing can this basically this whole function can is already been implemented in PyTorch, and that's called tensor dataset. All I have to do is import tensor dataset, which I have done in the top, and I'm just passing in the X train and Y train tensors and seeing for myself what is happening, and it gives the exactly same thing, right? Okay, so that is your tensor dataset from PyTorch. It makes the things so much easy. Okay, uh, that's done. And now what we have here is a data loader. Now what data loader is, basically it's a wrapper on your tensor dataset, and what it essentially does is take your training data, or whatever data set that you have, and it has many parameters inside, built inside, right? It has the training. I'm using batching, so it's like a 16 I'm using for batching, and yeah, and shuffle is equals to true. So how you want your data to be, so that all things you can specify using data loaders. Cool. Okay, just give me a second. Okay, so coming back, so what if I do this? Let's see. Okay, there was another way to actually, you can see one more thing. I want to show you something actually. See this training data, right, from tensor dataset. You can see all of them using this next, and it's a iterable. Okay, please look into what iterables and iterators are. You can actually see for yourself what they are using this too, in a sense. Okay. Okay. Hmm. Cool. Yeah. Hmm. Okay, let me see one more thing. Hmm. We're talking about data loaders. So until now we have used the whole training data in every training step. uh, it has been batch gradient descent all along. What does it mean is we're taking all of the data and uh, basically training it at once and updating the weights, right? This is fine for like a very small data set, sure. But as we just have 80 instances in our system, right now. But if you want like a serious about it for training, we will have to use mini batches. As I already told you, what are mini batches is basically a subset of your training data set, and you train it on those subsets first and then do the updates, and then the whole epoch is done. Then one epoch is basically when you go through all data set, then one epoch is done, right? So what we want to do is mini batch gradient descent. So you must have noticed one thing, some peculiarity that you might face is it's always SGD, right? Even if it's mini batch, even if it's batched or like stochastic. Gradient stochastic is basically you're taking one data point in, updating the parameter, another data point in, updating the parameter, instead of taking all the data or mini batch into it and then updating data. So that is what we call a stochastic gradient descent. Although every one of them are using the stochastic gradient descent, essentially the batching and all that stuff happens here in the custom data sets and data loaders and all that stuff. So we have the same algorithm for all of them concerning the optimizer. Okay, yeah. So what was I saying? Yeah, thus we need mini batches, and so basically the slices of the data set, right? So uh, we will tell which data set to use, the one we must build in the previous section, right? And the desired mini batch size, and if you want to shuffle it, that is the three parameter that we had. So important point here is, in the absolute majority of classes, you should set shuffle equals to true for a training set to improve the performance of gradient descent. There are few exceptions though, like time series, of course, because things are coming and the sequence matters, right? Where shuffling would lead to data leakage. Data leakage uh, is not like data is leaking somewhere. It's basically like when your training data set is getting some information from your testing data somehow, something you did that is making your training data set know what your testing data set already has. So it's learning your testing data set as well, or validation set data set for that matter. So that is what we call a data leakage, right? So you don't want that bias coming in your data set, training data set, from your testing or validation data set, right? So always ask yourself, do I have a reason to shuffle the data? In such cases that we have, shuffling is okay, it's good. You want to make have a variety of every batch. Basically, it's like, if as you are batching, every batch should have all variety of data points, right? It shouldn't be like this for particular batch. The first batch of the data set has all the yes values, and the second batch all the no values. You don't want that. You want equal representation, at least in both of in all the batches. So shuffling can help you in that. If it's a multi-class model that you're creating, there are multiple classes, 1 2 3 4 you want to classify into, like image detection, image classification of a dog and a cat and a turtle and a fish or whatever. So you want the equal representation in every batches. Okay. Okay, so there is more to dataset than than meets the eye. It is also possible to use it together with a sampler to fetch mini matches that compensate for imbalance classes. For instance, I was talking about that, right? So we're not going into that. So let's see how you should batch something. Okay, so our loader will behave like an iterator, so we can loop over it, fetch a different mini batch every time. As I already showed, it's an iterator. That is what I was showing here, right? So how do I choose my mini batch size? It's typically in the power of 2. Most people do it 16, 32, 64, 124, 128 and all that stuff. Like a lot of people have choices of 32 is the choice of a lot of people. Okay, some more complex models can use even larger sizes, although sizes are usually constrained by hardware limits rather than the limits of the numbers. But you have some video or something, or big corpus of text coming in. You don't want to put in 128 into a batch, right? So much data cannot fit into your hardware, so your hardware limitation will kind of define your size of your mini batch, right? So in our example, we are taking 16. So 16 is the batch we are using. Okay, so as we already know, uh, so basically it will have how many batches? 5 batches it will have, and every batch will have 16 data set. Okay, let's paint it out a little bit in our brain. So you have this big data coming in, 80 of them. We are dividing it into 5 batches of 16, 16, 16, 16, 16. Okay, that is what we're doing. This whole thing is 80. It's for what? It's training data set. Okay, we're gonna do that, and you did that. Let's see. Now I'm gonna run this. So data train loader has been already done. All I'm gonna do is show you now what it is. It's again a object or function, but it's, as I showed you, it's an iterable. So what we can do is actually we can take this like this and see for ourselves every single one of them. So you can actually see for yourself. Okay, wait. What I can do is I can take this whole thing and do a interactive session right here. So it's like a Jupyter module that runs code from my actual py file. Uh, so it's running all the code till that point. So what I can show you in there was because it's a little cluttered here, so you won't be able to see what's going on inside, right? Okay. There are a few of the things we don't care about that. What we care about is this guy. This guy is what we care about. Okay. Enter. Yes. Let's see. Go to the text editor and see for let's do this. Okay. What do you see? You see, where is it? To training data. Let's also see what the training data holds for our own understanding. So your training data is, the first one goes like this. If I take, sorry, okay, I cannot do that. This is also like a terminal, so you can just do upper arrow and get the code from there. Okay, so what I can do is for I in this, I just want to print the I. Print the I. If I do that, okay. A lot of them are there. So let's see what is looks text editor. You can see 80 of them are here. Okay. So what you see here is, if you check this, will open this as well. So let's keep it here like this and keep this one also here like that. Okay. So you see 80 of them. It's coming from what? It's coming for tensor data set this time. That is train data. Okay. This is what the output looks like. And secondly, we have the train loader that comes from data loaders, and you can see what it is. So this is the first element of that. So first element has what? An array of 16. If you count this, is exactly 16 numbers of training and 16 number of validation. I hope that makes sense. So this is the training set and this is the validation set in one. Okay. If you want to see the whole thing, you can do the same thing that I did before. Instead of this, instead of training data, what you can say is train loader. That will help. And if I go like this, okay, now let's see in the editor. Now you see there are 5 batches. So this is the first batch. This is the first batch from here to here, and it has 16 samples. That is our batch size, right? Batch size 16. So 16 samples of training and 16 samples of testing. So in that's what it is. And then this is second one, the first batch, second batch, third batch, fourth batch, and then finally the fifth batch. Okay. Yeah, so let's just plot it. Like, let's see what we have. So what it's doing is tensor data set is basically the variable that we have for that is train data, right? This dude is putting out basically every single one of them is a pair of x and a y. Okay, so it holds all the x and y's like this. But what a data loader does, which is your uh, train loader, it is actually taking your 16 samples from the x. So it goes till 16, right? And then and y also is takes like 16 of them, something like that. I'm just giving a idea of what it looks like. Okay, so in a sense, now the big batch, this was something like if the data set, right? It would be x and it would be y. So it's cutting from here and then here and here and then here. So 1 2 3 and this is the fifth one, right? So 16 samples coming in, 16 samples coming in, 16 samples, of course. Okay, so five of batches are there. That is what data loader is doing. I hope that makes sense now. Okay. Oh, okay, sorry. Okay, let's get moving and let's keep on doing this. We are again data preparation. We are just doing all that at once, doing our data preparation, blah, and train loader is set. Let's do the training again, but this time what we are going to do is we're going to use the train loader, that is dataset loader, and we are going to do mini batch training. Okay, so setting the epochs and the loss, we have the mini loss coming in. So now as it's an iterable, you can actually see the x. So I can actually show you this one, right? It's pretty cool. We can put this um, like the no, I can copy this. Where is it? Yeah, paste it here with also print what x batch comma y batch is, and if I do enter, you see exactly what it is. It's the same thing, right, that we saw before. Okay. And that is it. Give me a second. My eyes are watering. Okay, sorry for that. Let's get back to what we're doing. Yeah. We're taking the x and the y and then putting in. So all the x batches now are put to device. That is, if you have a device. I don't have one, so we are not using GPU, the CPUs. And you can also see the x just to see the x batch. You can see here, like, yeah, that is what it looks like. The shape of it. Shape is 16 count. That is what's expected, right? It's taking the first batch. Okay, from that big data set that we had. From this big data set, we are just taking this first block of x and y. Okay, cool. Uh, let's go ahead. Again, we are putting it in the this perform training steps, and it will train the whole thing once and give out the results. And we have this mini batch. So mini batch loss is this much, and we are keeping a track of all the losses. Basically, in a sense, we are putting it here. So this is a mini batch losses we are tracking. The first mini batch has given this loss, so I'm appending it right there. So I'm gonna step over all these things. Second batch has come in, and we have calculated the loss for the second batch and appending it again. Third batch is here, and the fourth batch is here, and the last batch comes here and appended and done. Okay, all of them are done. So you can now actually see what this looks like. losses, right? Yeah. So there are 5 of them, 5 losses, and you can clearly see the losses are going down: 0.005, 0.001. Okay, this I mean, it went high here, but yeah, that kind of what do you say, stochastic behavior. Stochastic in sense means random. So such random behaviors are expected when you have such small data sets and such small batch size also. So, and we just had like what, the first loop has just done, first uh, epoch has just been done, right? So yeah, so we are just seeing, we are taking the mean of the loss. That is what this is the actual mean of the loss, and again we are appending it back in the so this completes the first epoch. So we went through the whole data sets, did how many updates? 5 updates are completed on 5 mini batches. Okay, now we are going to the second epoch, and as it goes inside, okay, I'm gonna show one more, that this one more, that's it. Second batch comes in, third batch, fourth batch, and this is the last batch, and there it goes. Empties the whole thing, and yep, you can see the loss has changed. The numbers of the loss have changed. Yeah. So I'm not going to do those 1,000 times. Okay. So I'm just going to run it once, the whole model, and model has been, okay, it's running. Wait, doing a lot of updates, right? Because right now with every epoch, you're doing 5 updates. So it's like 5 into 1,000. So 5,000 updates are happening right now. So, okay, the thing is done, and you can see the loss. You can see the loss is right here in front of you, and you can also see the model state also, right? So if I see the model dot, sorry, model dot this has been trained. Cool. Yeah, so we are trying to functionalize everything. We are also seeing the losses, so let's see the losses. Yeah, this is the losses. It's a big number. So it started off with 0 loss, sorry, the first iteration. So there are almost 5,000 of them, right? If I see the length of this, in the 5,000, there are 1,000 of losses, right? Because every epoch's 1,000 of them. And what you have here exactly is, if you just see the last one, you will see what exactly is the last 1,000. I mean, yeah, it's an error, right? Because it's not 99. Okay, and 99. This is your loss at the end of the training. Okay, because you're appending into the losses one by one. Okay, so mini batch in a loop. Let's do the whole thing that we did here, but let's again functionalize it, kind of create a wrapper around it. Okay, so let's do this. Basic things, it's not nothing crazy here. We are just functionalizing the whole code that was here, from here to here, right? Here till this part. We are functionalizing the whole code, the whole thing from here to here. So you can just pass it to the epoch thing. Okay. Again, same thing happening. It's going into the function. I'm not going to do this. I'm just going to play. Okay. And again, it's taking time. Okay. Done with the training. Okay. Now let's do some random splits. Okay. Right now we had the training set we are using directly, right? What if we are doing more of it? So basically we have our train loader and our val loader also. We are not doing any validation as of such. So we will do this validation soon. So for that we are doing this splits. Okay. Okay. Any more function, any more information that I can give on this is like, so why don't we just use, let's say a loader is there, right? So we can just say list of train loader. Let's say this one. Why can't I just use this? I mean, it's giving the same thing, right? It's actually exactly the same thing that is given by the iterator, right? I can use that too. But you will get as a result a list of 5 elements, of course. That is all 5 mini batches. Then you could take the first element of that list to obtain a single mini batch as example above, right? But it would defeat the purpose of using iterables provided by the data. that is to iterate over the elements, that mini batches in this case, one at a time. So to, if you want to really understand what that mean is, please do go look up iterables and iterators in Python, so you have a better grasp of what exactly means. Okay, so yeah, we are done with what that is, and the inner loop was also done. So few other side notes I might give. uh, Firstly, a few points to remember and a few side notes is, we add an inner loop to handle mini batches produced by the data loaders. Okay, we send only one mini batch to the device as opposed to the entire data set, so it also is memory efficient, right? For larger data set, loading data on demand into your, let's say, CPU tensors, okay, inside data set, and like the under the dunder method of get init method, and then sending all data points that belongs to the same mini batch at once to your GPU device is the way to go to make the best use of graphic card RAMs. Okay. However, if you have many GPUs to train your model on, it is best to keep your dataset device agnostic and assign the batches to the different GPUs during training. Okay. So we perform a train step function, that was a function, a wrapper function on training the models, right, on mini batches, and appended the losses and all that stuff. That was done. And after going through all the mini batches, that is at the end of the epoch, we calculate the total loss and we average the loss out for that, and we get one value of the loss. Okay, that's it. Cool. Okay. I hope you noticed one thing, that is, it was taking longer to train the model now. The answer is basically the training time is longer now because the inner loop is executing 5 times, right? There are 5 updates happening for each loop. So there are like basically 5,000 updates happening, as I already told you that, right? Cool. Yeah. Uh, okay. Okay. So let's do some other. We are gonna split the whole thing, and let's get with that. Splitting it, train X, and all that stuff, just so you are familiar. X train X. This is shape is again 100, and so both of them are 100. Now we're splitting it. So basically a simple formula of splitting the whole thing. So now you have uh, n train, and so n train dot shape. Sorry, it's a list. Sorry, so I will have to see the length of this list, right? Len of this list is, okay. What happened? Okay, it's a number. I'm so sorry. It's just a number, and we are putting it in the random sampler. We are using random sampler to say basically this has to be. So I can just do this, and now it will work. Train data. Train data dot shape. Okay, is it a list? Okay, it's a loader. Basically, we are passing that into your data set. Random split is basically a Python's version, and it is using dataset inside it. So it returns, if you see what it returns, it returns a subset of dataset itself with all the indices. So basically tensor datasets is doing just like that, and we are passing that dataset into uh, into a data loader with a batch size of 16, and the shuffle is true. Okay. uh, I can give a little more insight into what it means exactly. Okay, so uh, PyTorch's random split method is an easy and familiar way of performing like training and validation split. So far, we have been using the xtrain tensor and ytrain tensor built out of the original NumPy array. Okay, now we are going to be using the full data from NumPy to build the PyTorch dataset first, and only then we will split the data from the. Although there are reasoning behind my choice of like the 42 basically as the random seed, which is actually random seed is something that you can do. Here you can see some different values you can put it in, and you can have reproducibility in your code, right? So we have the whole code loaded in. Making tensor out from the full data set is done. Performing train validation split in PyTorch is done. Creating a data loader for the validation test is done. Okay. Yeah. Now let's go and see and evaluate our model. Okay. A little bit. So evaluation, again, we are creating a higher order function, a wrapper around the evaluation function, make val step known. So what you have is you train a model using the training steps, and then you evaluate it using, once the model is trained, you take the model and evaluate on your evaluation sets. Okay. So essentially what it means is, so once you take the training set, training, right? Training, and then you train the model. So in your case, 80 instances were trained, and model has been trained. Its parameters are W and B are set. Okay, you found the approx value for W and B. Now what you do is take the same model and pass it through a evaluation function. What evaluation will take is, here you are taking in the training, here you are taking in, let's say, the training data, right? Here you will take the valuation data, and it will spit out some numbers, the metrics that you want to use, accuracy or something, right? So that's how it happens. So we are creating, so let's do this. Okay. So you see one thing here, the model is in an evaluation mode. Okay, I encourage you to actually go and read up what it means, but for now let's just see. So we use the model eval method. The only thing it does is set the model to an evaluation mode, just like train mode that we had in our training set. So the model can adjust its behavior accordingly when it has to perform some operation like dropouts and all. Basically, that's where we don't want dropouts when we are doing our evaluation, but we want the dropouts when you are doing our training. So such behaviors can be uh, like specified using this mode. So right now our model is an evaluation mode. Okay, cool. Okay, so dropout, just so I can give it, dropout is a regularization method commonly known for reducing overfitting. Basically what you do is, if you, let's say, dropout, if you know what dropout, if you don't know what dropout is, basically if you have a neural network, let's say this is a neural network, a big one. Okay, a lot of neurons and coming in, blah blah. So what you do is, with you assign a probability of what. Probability is basically, if you have 0.2 probability, that is 20% of time in while you're training, few of this uh, neurons will be cancelled out. Basically it will be zero, so there no connection, no data will flow through them. Even if it does, it's basically zero, so the output will be zero. So that is what we call a dropout. So if your model is overfitting, that is, if you must have come across like decision tree or something. So what happens if we extend decision tree to infinity? If it creates as much nodes as it wants, what happens is it overfits on the data, that it learned basically everything about the data, and overfitting is a big problem, right? So in that sense, we are also kind of, if we delete those nodes in the decision tree, then we see that overfitting can be reduced. Okay, so it's in kind of a same idea here, that if we delete the neurons, in a sense, in our training process, we can maybe uh, essentially reduce our overfitting. That's what it means. Okay, so look up what overfitting is. It's pretty cool. And dropout is, so that happens. So it's the main reason for it, since it requires a model to behave differently during training and evaluation. In a nutshell, dropout randomly sets some weights to zero. That's what I do during our training only, but in our evaluation we don't need that dropout. Okay, we will get back to what dropouts are in the future videos. Okay. Okay, yeah. So what would happen if, let's say, the behavior persisted outside of the training level, let's say dropout happens, you would end up with possibly different prediction of the same input, since different weights would be set to 0 in your evaluation. It would ruin your evaluation, right? So if I am evaluating and it randomly sets some guys to 0 in the second time I'm taking in the in the data set coming in, and it assigned this dude as uh, 0, then you will have different results for evaluation. That would be a very, 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 what do you say, bad way of evaluating your models, right? Okay, so that's what dropout is in a sense, and why we use eval and train. Okay, cool. So we are creating the higher order function. Basically, we are taking in the data set and passing it into the models, compute our model's prediction, so forward pass, calculate the loss, and also return the loss. So there is nothing like optimizer is not there. We are not doing any optimizer dot step, optimizer zero grad. None of that things are happening, right? Mm. Of course, it's evaluation. Just passing in the data. Okay, so that's done. We are initializing a model, optimizer, loss function, going inside the model and passing all of them. So let's see what is happening here. There we are setting all that in. It's returning the inner function, right? This function is returning another function with, okay. And so now this train step function is a callable for the same thing we are going to use. So that was a train name. Now we are doing for the evaluation. So evaluation don't need an optimizer, so there's no parameter called optimizer here, right? So only the model and the loss function that you have. Cool. Yes, both of them initialized. Let's do some training. So we have already created a lot of helper functions. So we are keeping track, just so you know, when you are doing the whole process, this is what everything comes in, right? You are training it, you are evaluating it, both of them are coming in. So proper model has been created in a sense. So in this scenario, you have to keep track of both the losses, that is your training loss and your evaluation loss. The losses here, this one denotes the training loss. So when you're training, there are losses that you're calculating, and this evaluation, what are the losses that you're calculating? Okay, so yeah, going in, same thing happens. I'm not going inside. We are creating the mini batches and the training is done. So mini batch training happened for the first epoch, and now you see there's something here, torch dot no grad. Why is that so, right? So if I were to tell you what it exactly means, use no grad as a context match to prevent gradient accumulation. Just like we had to manually do like optimizer zero grad. Why we do that? We don't want any kind of accumulation of gradients in the computational graph, right? Evaluation also, we don't need any kind of gradients because we are not updating anything. We are not calculating gradient for anything. So what we do is we evaluate always inside this function. So no gradient is no gradient is accumulated, no gradient is calculated in this scenario. Okay, was I saying accumulation? I'm meaning gradient computation is happening. So no gradients need to be computed. So that is what it means. Okay, so even though it won't make a difference in our simple model, it is good practice to wrap the validation inner loop with its context manager to disable any gradient accumulation that we may trigger. So gradient belongs in training, not in validation steps. Okay, make sure you understand that. Okay, you can understand what context manager is. uh, Context manager is something like in a program language, the usage of resources like the operations or database connection is very common, but there these resources are limited in supply. Therefore, the main problem lies in making sure to release them these resources after usage. If they are not released, then it will lead to resource leakage and may cause the system to either slow down or crash. So it will be helpful if user has a mechanism to automatically set up and uh, tear down basically resources. So that's what you call a context manager. So you see this with dash. So that is kind of thing that's happening here. Okay, cool. Yeah, so let's do some evaluation. Let's go inside this batch take the first batch that we had, see for ourselves. This is seeing the loss for itself. No training is happening here, and append it here inside. Okay, there are 5 of them, so 5 of them I have to do. Okay, done, returned, and we are appending it here. So let's see what the losses are after the whole one thing, right? So this is a training loss. This is your validation loss. I mean, I haven't done that right. Okay, now it might work. Oh, sorry. Okay, empty. Okay. What about this val loss? We are out of the loop, right? Okay. Now you see both of the losses are there, and that's cool. Why can't? Why isn't it updated in here? Okay, I'll see what problem is there. Okay. Mini batch done. Again, going in, mini batching the whole thing up. So we are using the same function to mini batch for both training and testing. I mean, that is uh, simple, right? Then again, adding in, putting in Dan. Let's see what we have. Yeah, we have it appended. We have the loss coming in. This is the actual loss, right? Okay. Yeah, so that's that. I am not doing it more, so I'm just gonna do the whole thing at once, and then we will probably just see a graph of both of them. So we are just plotting a graph where the losses for both the training loss and the validation loss, both of them are there. There are scale is your log and epochs and losses and all that stuff. And let's run this. Okay. Return. What happened? Seems like there was a problem. Okay, it's just a graph actually that something. Give me a second. Say- Okay. I'm trying to show you the graph for uh, both the loss and both of them. Okay. Almost there. Let's open it up. Yes. This is how it looks. The training loss and the validation loss, both of them are right here. So as you can see, the training loss is lower than the validation loss. So that's because of little bias is there. Little bias. The model is a little biased towards your training set, which is understandable in the scenario. Okay, so we have almost done all that we had to do to make a very simple regression model. We're gonna do more of these. We're gonna come up with more topics, and probably I will also do some coding thing as well. How to basically code stuff in much more modular way, and going much deeper into how things work, hopefully. And let's after this we will do a classification problems, as we had done regression problem, and we will get into computer vision a little bit, classifying images and convolutions and transfer learning, what are vanishing gradient problem, exploding gradient problems, then sequential datas, RNNs, CNNs, and hopefully we have sequence models coming in, transform models coming in, right? We will go down that route as well. Okay. Uh, okay. Thank you for joining in. See you the next time.